right, so I'd like to now put some of these vector ideas to work in a very important kind of example to illustrate a physical principle that's naturally expressed with vectors. This has to do with moments and the centers of mass. And it really goes back to Archimedes and this famous law that he discovered called Archimedes' law of the lever, which tells us when two masses on a lever balance. Okay, so here's a lever, and we have some point there like this, and we have some masses, one on this side, one on this side, and we're interested in the situation when the thing actually balances, doesn't fall over. Okay, and he noted that the relationship that's required for balance is a very precise one in terms of the two masses, let's call them M1 and M2, as well as the two distances, D1 and D2, from the fulcrum, the place where everything is trying to balance, to the bottoms of the masses. Okay, so that's D1 there, that's D2 there, and this is his crucial relation, that the lever will balance precisely when M1 times D1 equals M2 times D2. When the product of this mass times that distance equals the product of this mass times this distance. Now this has the effect that, let's say we do have a situation of balancing, and suppose that the mass M1 is, say, doubled. Okay, suppose you have twice as much mass there. All right, so that one of these sides of this equation will be doubled. Okay, so suppose that we want to still keep things balanced. That means we have to double somehow this side here. So one way to do that would be just to double the mass M2. But suppose that you're on a seesaw and there's only you there, and so somehow you have to adjust to the fact that there's now two people sitting on the other side as opposed to just one. So what you could do is you could multiply D2 by 2. If you move out to double this distance, then this quantity, this total, actually it's called a moment, will be still the same as this one on this side. And so you will still balance. Okay, so the point is that if you can compensate by increasing the mass by, say, decreasing the distance, or vice versa. So it's a very powerful relation, and really is responsible for all kinds of wonderful things in physics. Now we're going to look at this 2,300-year-old relation from a very modern point of view using vectors. It turns out that the language of vectors is ideally suited to not just reframe this, but actually to allow a broad extension of this principle. So the key idea is to think about something called the moment of a mass around a point. So let's call this point F for fulcrum. And we have these two masses, M1 and M2. And now let's think not in terms of distances, but rather in terms of displacements or vectors. Okay, so here we have a vector V1. This is the displacement from this point to the point right under the mass M1. That's the vector V1. And V2 on the other side is the vector, which is the displacement from F to the point underneath M2. So if we multiply a mass times a vector, we get another kind of vector object, which is called a moment. It's a different kind of vector. It's not really a displacement vector anymore because the displacement has been multiplied. We've expanded the vector, or perhaps contracted it, by multiplying it by the mass. So the mass times the vector is a new vector called the moment of the mass around F. Now in terms of these moments, the balance occurs when this relation is satisfied. When M1 times V1 plus M2 times V2 equals the zero vector. This is a rewrite of this original equation in the language of vectors. And you can see that we've exploited the fact that vectors have direction, because over here the distances are necessarily positive. But over here with these vectors, vectors can be positive if they're in that direction, and they'll be negative if they're in that direction. So that allows us to replace this equation with this equation where everything is on the left-hand side. m1v1 plus m2v2 equals 0. That's the condition that we require for balance. This is a very powerful way of writing. This is actually a much better way of thinking about the balance condition, or Archimedes' law of the lever. So let's give an example. Suppose that we're in the one-dimensional situation and we have three masses now. And we know exactly where the masses are. So there's a mass of 10 at the point whose coordinate is -1. There's a mass of 3 at the point 1, and there's a mass of 5 at the point 4. So we're assuming masses of 10, 3, and 5 at -1, 1, and 4. And I might not write respectively. Usually one writes respectively, alerting us that this one goes with this one, and this one goes with this one, and this one goes with this one. Let's just assume that if I don't say respectively in such a situation, that's what I implicitly mean. Okay, so a natural question is here, where is the center of mass of this configuration? What does that mean? Well, in this case, it means that we want to find a point where we could put a fulcrum so that this collection of three masses will balance. And we're assuming that the actual rod that things are positioned on is weightless. It doesn't really contribute to the equation. It's only these three masses that are involved. Well, each of these masses will exert a turning force on the lever wherever the fulcrum is. Let's say the fulcrum is at some point whose coordinate is x. Okay, so what we're going to do is we're going to write down the moments and require that the three moments add up to 0. That's the balance condition of Archimedes extended to the three masses. So the sum of the moments will be what? So the moments are these expressions here. m1 times v1, m2 times v2, and m3 times v3, where the vectors are the vectors emanating from the fulcrum to the various positions where the masses are. And we really want that vector sum to be equal to 0 for things to balance. That's Archimedes' law. Okay, so the first moment, there will be a mass of 10. And what is this vector here? The vector emanating from x going to -1. Well, there's the vector there. Okay, that bracket means vector. And it's a vector whose components are the difference between the coordinate here, which is -1, and the coordinate here, which is x. That's how we take the displacement vector. Final position minus initial position, all in a vector. The second moment exerted by m2 will be the mass, again times the displacement vector between x and where the mass is. In other words, we have to take 1 minus x, the difference in the coordinates between those 2 points. And the third moment involves the mass 5, as well as the vector going from x to 4, and that's the vector with round brackets containing the number 4 minus x. Okay, so this is exactly a kind of expression that involves the arithmetic of vectors, because we're multiplying vectors by scalars and we're adding up vectors. So everything just combines in the obvious way. We're going to get a single big vector with what inside it? Well, how many x's are we going to have? We're going to have minus 10 x's here, minus 3 x's there, minus 5 x's there, a total of minus 18 x's altogether. And what else are we going to have? We're going to have a minus 10, from there a plus 3, and a plus 20. That's a total of plus 13. So that's the vector, that's the sum of the moments. One moment for each of the masses. And that vector, according to Archimedes' law, according to this physical law, ought to be the zero vector. They all should cancel out in order to have perfect balance. In other words, what's inside here has to be 0. That means that the x has to be 13 over 18. And so the center of mass that we found is F, which is the point 13 over 18, which is somewhat where I kind of guessed it would be, somewhere between 0 and 1, a little bit closer to 1. That's the point where those three masses exactly balance. And it's a very powerful general kind of idea. And it also works even in higher dimensions. In particular, we can extend it to 2 dimensions as well. All right, so here's a 2-dimensional version of the same kind of problem. We're working in the plane and we have 2 points, A1 and A2. And we're assuming that we have masses at those 2 points. A mass of 80 at A1, a mass of 30 at A2. The point A1 is the point 3, 2, right there. And the point A2 is the point 1, 4, right up there. Now, there's a question of how we should think geometrically or physically what is represented here. So if we think of these 2 points as sort of being on a plane, so there's one point and there's another point, there's the segment between them, we really should think about these 2 points as being horizontal. Okay, so think about the 2 points as horizontal. So we're kind of looking down on the picture like this. Okay, so we're thinking about these 2 points as points, and this is a horizontal segment, and we're interested in where these 2 points balance, where we could put our hand underneath these this segment with these 2 masses so that it balance. Okay, that's what we're doing. So it looks maybe like this is vertical. That's not vertical. The whole thing is horizontal. We're looking at it horizontally like this. We're trying to figure out where's the point of balance between these 2 masses. We expect the point of balance, of course, to be on this segment. I mean, our hand should be under the segment somewhere. But where under the segment exactly? Okay, so this is a very natural question. Where is the center of mass, F, equals, say, x, y, of these 2 masses? And then we're assuming that the rest of everything is weightless, has no mass. In particular, the segment is massless. Okay, so let's put the point F temporarily here so we can sort of see it. So here's the point F with arbitrary coordinates x and y. And what we're trying to do is we're trying to find where that point has to be in order that the moment of this mass around F plus the moment of this mass around F add up to 0. Okay, so there's really 2 vector quantities. There's the moment of this mass around F, that'll be a certain vector. There's the moment of this mass around that point, that'll be another vector. We want those 2 vectors to add up to the 0 vector. Okay, so here's our equation. For balance, we want 0 equals m1, which is the first mass, times v1, that vector, plus m2, the second mass, times v2, the second vector. We want that all to be 0. Okay, the mass m1 is 80. And what is this vector v1? Well, it's the vector going from F to A1. Okay, that vector there. And we know how to take the displacement vector. It's the difference between coordinates. We have to take the coordinates of A1 and subtract the coordinates of x. So we're going to get 3 minus x for the x coordinate and 2 minus y for the y coordinate. That's the vector v1 from here to here. And similarly, the mass m2 is 30, and the vector v2 going from F to A2 will be the difference of coordinates, 1 minus x and 4 minus y. So this multiple of that vector plus this multiple of that vector should hopefully give us the 0 vector, which is the vector 0, 0. So what do we get when we do the arithmetic? When we do multiply what's inside here by 80, multiply what's inside here by 30, and then add those two vectors in the standard way of adding vectors that we've described. Well, the first coordinate is going to be 80 times 3 minus x plus 30 times 1 minus x. So a total of what? 80 times 3 is 240 plus 30 was 270. Minus 80x, and there'll be minus 30x, gives a total of minus 110x. And the y coordinate is 80 times 2 minus y, which will give us 160. And then it'll be a 30 times 4 minus y, so that'll give us another 120. So a total of 280 is a number. And how many y's? Minus 80 y's, minus 30 y's, so minus 110 y's. So this has to be 0, and this has to be 0. Easy to solve. That means that x has to be 270 over 110, or 27 over 11. And y has to be 280 over 110, or 28 over 11. So that is the center of mass. It's actually a point that's going to actually be on here. It's not going to be out here. That would be crazy. It's going to be a point on here, and it's going to be somewhat closer to this one here because the mass here is bigger. 27 over 11, so it's between 2 and 3, so roughly halfway, so maybe around there. And 28 over 11, it's almost the same kind of thing, sort of between 2 and 3, just a little bit more. So the cumulative point may be around up there. Okay, the center of mass would be right about there. Somewhat closer to this one because this is heavier, this one's lighter, but the two things will balance. So imagine the fulcrum there, there's a mass of 80 there, there's a mass of 30 there. We're finding that point there where the thing balances. It'll be closer to this side here, like a seesaw. There's a heavy person here, 80 kilos, lighter person here, 30 kilos. We have to put the fulcrum somewhere around here in order for there to be balance. That's what we've calculated using the vectors. So in our final example, I want to illustrate once again the power of Archimedes' vector form for the law of the lever. But now with 3 points in the plane. And I also want to do it in a more general fashion than previously. So in the previous examples, we were looking at particular values with specific numbers, specific masses, specific points. That's useful to get an intuition of what's going on. It's also very useful and important to get some kind of understanding of what things look like with general input. Right? Where we have input which is general, like a mass of M1, a mass of M2, a mass of M3 at points instead of mass of 45, 70, and 349. Okay? There's something useful about seeing the formulas with the variables representing the input quantities themselves directly. So that's what the problem is here. We have a very general problem of now 3 points in the plane, A1, A2, and A3. And they have general coordinates. So A1 is a point whose coordinates are x1, y1. A2 has coordinates x2, y2. A3 has coordinates x3, y3. And we're assuming general mass of M1 at A1, M2 at A2, and M3 at A3. And we're interested in what's the center of mass of this triangle. So it's a lot like the previous kind of situation. We have this triangle here. We actually want to think about it as being a triangle that's horizontal. Okay, imagine cutting out a triangle exactly of this general shape. And we're interested in where does this thing balance, assuming we have masses M1, M2, and M3 at the corners. It's otherwise weightless. So we're interested in the center of mass, and let's call it F, with coordinates x and y. So there is a possible place for it. Okay, so the crucial ingredients here are the 3 masses, of course, but also the 3 vectors. The vector emanating from the proposed center of mass to the point A1, let's call it V1, to A2, which is V2, and to A3, which is V3. So these 3 vectors get multiplied by the 3 masses to give us the 3 moments. And the sum of all those 3 moments has to be 0. That's Archimedes' law of the Liber. Okay, so here's the formula for balance. So that the sum of the moments, which is the sum of the products of masses times these vectors, FAI, FA1, FA2, FA3, equals the zero vector. Okay, I'm going to leave it to you as a little exercise to try to make this calculation if you haven't already done so. It's very instructive. To try to find out what the x and the y have to be. And here's the answer. Okay, so the point F turns out to be this one here. And the point x turns out to be m1x1 plus m2x2 plus m3x3 divided by the sum of the masses. It's the total mass. And correspondingly, the y-coordinate turns out to be m1y1 plus m2y2 plus m3y3 divided by the total mass. It's a very instructive and useful formula. Very important in physics, in fact. And it's very useful to see it in this kind of generality where we have general masses and general coordinates rather than specific ones. Okay. So in the accompanying text for the course, I'm going to give you a derivation of this so you can have a look there, but have a check also yourself, see if you can make the calculation. So we've covered a lot of material: vectors, displacements, centers of mass coming from thinking about not just displacement vectors, but also moment vectors. So we're connecting with physics, which is natural enough because calculus has a lot of connection with physics. And we're getting used to working in this two-dimensional world where calculus lives. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.